Hello all. In this video we will be studying about atomic radius in D block element. Before that, let's have a quick recap of what we have studied. Atomic radius along the period, it decreases whereas down the group it increases. Why down the group increases? Because number of shell increases, so effective nuclear charge decreases, and down the group atomic radius increases. Now the picture that today we will see how along the period in the D block how atomic radius is it decreases or is it increases, is it constant, and even down the group how it varies. The picture that you see right now, the whole picture, this is periodic table. These two, group 1, this is group, these are called as group 1, from 1 to 18, these are called as group, and from this part is called as period. These two are S block. All this thing we have studied, I am just briefing it again. From group 13 to 18 is called P block. And why they are called S block, P block? Because in the electronic configuration, the electrons, the last electrons are filled in S orbital. So all these elements are named as S block element. Similarly goes to P block, and this part, these are called as F block element, and these from group 3 to group 12 are called as D block element. So in this video we will learn the atomic radius in this particular block. So this is what I have zoomed. Now this period is fourth period. Okay, fourth period. This is fifth period. From lanthanum to mercury it is sixth period, and this is the seventh period. For D block element, there is one more name for each group, each period. The fourth period is called as 3D series. And why 3D series? Because if you see the electronic configuration, the electrons are filled in 3D orbital. Similarly, for this period, the electrons are filled in 4D. If you see, check the electronic configuration. So fifth period is also called as 4D series. So usually when we are talking about D block element, we talk on the basis of series than the period. This is period denoted as N, and these are series. Why series? Due to their electronic configuration. Hope this is clear, students. Okay. Moving on, the sixth period is called as 5D series, and seventh period is called as 6D series. Hope this is clear. One more thing you're supposed to know in D block element is that in lanthanum, which has atomic number 57, hafnium, which has atomic number 72. So can you see there is a big gap, 57 to 72, 14 elements are missing. In periodic table, there are total here from 57 to 72. All 14 elements are kept outside and they are named as lanthanide. Their atomic number from 58 to 71 elements, that totally it is 14 elements. They kept outside the periodic table, kept separate. These are called as lanthanoids. Why? They come after lanthanum element, so they are named as lanthanoid. Similarly it is from this part. Okay, similarly from 90, from electronic configuration 90 to 103, 14 elements are kept aside and they are named as actinoids. Why they are named as actinoid? Because they come after actinum. These lanthanoid and actinoids are together clubbed and called as F block element. So whatever you see in periodic table, this is lanthanide. Okay, the spelling is wrong. lanthanide, and these are actinoid. They are kept separate, that comes after lanthanum. Hope this is clear. And this is called 3D, fourth period 3D series. Fifth period of D block is called as 4D series. Sixth period ka D block elements are called as 5D series, and so on. Now let's see, this is the introduction of what is D block. Let's see what happens in the atomic radius in D block element along the period. First, let's see fourth period. In fourth period, we have elements here, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. There is no choice, you need to memorize this. If you want to solve any question in D block element, memorizing or in anything of periodic table, you need to memorize the periodic table. There are many tricks, mnemonics, but I prefer, see, when you can memorize the mnemonics, why can't you memorize directly the element? So that is how I take it. So any other way you can just see it, how to memorize this. So let's moving on. These are the fourth period elements of D block, and these are also called as 3D series. They have electronic configuration 3D10, 1 to 2, 1 to 10, and NS2. In all these elements, they have electronic configuration 3D 1 to 10 NS2. Only for chromium and copper, they have NS1 configuration. So this is 3D1, 4s2, 3D2, 4s2, 3D3, 4s2. It has chromium has a special electronic configuration. It has 3D5, 4s1. And why it is 3D5, 4s1? Actually, it was supposed to be 3D4, 4s2. Right? Because after D3, one more electron will fill. It will be D4. But in D subshell, maximum it can fill 10 electron. It is called fully filled electronic configuration. And its half is 5 electrons are filled. So if 5 electrons are filled, these are called as half filled electronic configuration, and these two both configuration are quite stable. So what they do is, the electrons of 4s2 is transferred to 3d4 to attain the stability. So the configuration is 3d5, 4s1. Hope that is clear. So moving on with manganese electronic configuration, it has 3d5, 4s2, iron 3d6, 4s2, cobalt 3d7, 4s2, nickel 3d8, 4s2. Here also same thing, copper. To attain stable electronic fully filled electronic configuration, it has copper has 3d10, 4s1, and zinc electronic configuration is 3d10, 4s2. Hope that is clear. Now let's see, in all this from scandium to zinc, what is the electronic configuration? So let's begin from scandium to manganese. So scandium, titanium, vanadium, chromium, as usual, how atomic radius along the period, atomic radius decreases. It follows the same trend. Okay, along the period, atomic radius increases. From iron, cobalt, nickel, all have same atomic radius. It has similar atomic radius. From copper to zinc, it is changed. What we know, atomic radius along the period decreases, but here it increases. Zinc has greater greater atomic radius. Let's see how. From scandium to manganese, if you see the electronic configuration, if you see the orbitals, here 3d1 for scandium. For titanium it will be 3d2, so 1, 2. For vanadium it will be 3, 1, 2, 3. So if you see, no pairing take place. There is no pairing. Till 3d5 also, if you see the configuration, there is no pairing. 1, 2, 3, 4, 5. No pairing happens here. And as no pairing is there, as effective nuclear charge increases, size decreases. Why size decreases? There is no electron repulsion also. So along the period, atomic number increases, and along the period atomic radius decreases from scandium to manganese. Why? There is no pairing happening. So when effective, here there is a nucleus and we have electrons here. So when as effective nuclear increases along the period, attraction takes place as there is no pairing, so size decreases. Hope that is clear. From iron to cobalt, this is for scandium to manganese. Iron, cobalt, nickel. Here if you see 3d6, the electronic, if you see the pairing 1, 2, 3, 4, 5, 6, we have here electron pairing. When the new electron appears, there is electron repulsion happening. But this electron repulsion counter strikes the Z effective, the effective nuclear charge. As such, they remain almost same. Iron, cobalt, nickel, because if you see 3d7, one more electrons are filled there. Again these have electron repulsion. Also there is along the period effective nuclear charge increases. So both the strength or both the effect compensate. The electron repulsion along the period increases because pairing is taking place, and also Z effective along the period also increases. These both effect compensate each other. So along from iron to nickel, the atomic radius almost remains same. Whereas copper and zinc, here copper, if you see, we have full-filled electronic configuration. They have fully filled in the sense, if you see 3d10, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All are fully filled. If you see, pairing is there and there is electron repulsion also. But this electron repulsion is higher, very more, such that the Z effective is less dominating. The effective nuclear charge on the outermost electron, there is no effect, because electron repulsion is so high that radius is increasing. Increase in radius happens. Hope that is clear. If you have any queries, you can comment down in this comment section. Similarly for zinc, why zinc the atomic radius is more? Because here 4s1 is there and here 4s2 is there. Again they have electron repulsion. Such electron repulsion makes the size far apart. There is increase in size and Z effective has no such effect on the outermost electron. So hope this is clear. So here is the wordings. In D block, along the period size decreases. This we know. Till middle, that is from scandium to manganese, the size decreases. The regular trend of the block remains almost constant till nickel. Okay. From iron, cobalt, nickel, they have constant atomic radius. Why? Electron pairing is there, due to which electron repulsion also happens. Z effective also increases, but these two effects compensate each other because pairing is happening. Then again size increases. Why size increases? All are fully filled. Electron repulsion is very high, such that size increases. Z effective have very less effect on the outermost electron. Again, from scandium to manganese, atomic size decreases due to effective nuclear charge increases, is more prominent than shielding effect. Hope this is clear. Iron to nickel, they have constant size, whereas copper, zinc, atomic size increases due to electronic configuration. Now you might have question, ma'am, See, scandium has higher electronic configuration if you move along the period. Cobalt zinc also has higher atomic size. So among scandium, copper and zinc, who has the higher atomic size and why? Experimentally they found out this graph. So this is for 3D series, this is for 4D series, and this graph is for 5D series. Let's only see for 3D series. This point represent for scandium, this point represent for zinc, and this point represent to copper. Though zinc and copper has a higher atomic radius is very high, but it is not as high as that of scandium. So scandium has, among all the 3D block elements, scandium has higher atomic radius. Then you have to see zinc and copper. In zinc and copper, who has higher atomic radius? That is zinc. And last comes copper. After copper is the rest of the 3D block element. So this question may appear, it has appeared, I am not sure in which paper, but this thing has appeared. So among scandium, zinc and copper, scandium has higher atomic radius then zinc, then copper. And in zinc and copper, why they have higher atomic radius? Because they have fully filled charge, electronic configuration is very higher than that of Z effective. So this is about along the period. Let's see down the group what happens. Again, this is 3D block element. This is 3D series, 4D series and 5D series. If we see from 57, okay, this I have written it wrong. Something I have done. Lanthanide, actinium. Okay, now it is right. Next one is, if you see from scandium, titanium, vanadium, this is 3D series, and we have 4D series and 5D series. Okay. Okay, now what happens here? Here it is wrong. I have written it wrong here. It is not supposed to be atomic radius. Okay, now we have yttrium here and we have a zirconium here. This is 5D series. In 6D series also we have here F block element. Now from lanthanum we know down the group what happens. Atomic radius down the group atomic radius increases. Why atomic radius increases? Because N increases. Okay, so now down the group atomic radius increases. So scandium have less atomic radius and lanthanum has higher atomic radius. Why down the group increases. Even in titanium, zirconium, all this 4D series have higher atomic radius. Why down the group atomic radius increases. But here from hafnium to mercury, it is not the same. It is not 5D elements have higher atomic radius. And why this is happening? Because why this thing is happening? Because we have manganese, tactitium, osmium. Okay, now here the trend is from hafnium to mercury, the atomic radius is not increasing down the group. Let's see why. From lanthanum to hafnium we have something called as from 90 to 103. Do you remember in the initial start of the video I have said that is made up of lanthanoid series. They are kept separate. These are F block element. These here the electrons are filled in F orbital, and as we have all know, the F orbital is very poor shielding. If we see shielding order, S orbital is higher, shields very well, then P, then D, and F is the very poor shielding. So if I have here nucleus we have orbitals. Let's imagine this is f orbital and we have here sp other orbitals. So when electrons are here, these f orbitals are so poor shielder that this nucleus can easily attract this outermost electron. The z effective will be very high because f orbital is poor shielder. Hope that is clear. Due to which poor shielding, all the f orbital lanthanide series have contracted radius. Radius is less, contraction is seen, contraction of size is seen. Why? Because f orbital is poor shielder. Okay, so if you see among zirconium and hafnium, they have almost, due to contraction, due to f orbital size f orbital is poor shielder, contraction of size took place, so they have almost similar size. The 4d and 5d series have almost similar size. So if you see atomic radius trend, if you see the atomic radius trend, 3d, see down the group increases, so 3d 4d has among 3d series has least atomic size, 4d has higher atomic size, but in 4d and 5d they have, instead of 5d having higher size, 4d and 5d they have similar size. Why? Because due to this lanthanide series which is present here, they have f orbital. F orbital is poor shielder. Hope this is clear. Now let's solve one question which has been published in NEET 2022, that is decrease in size from left to right in actinoid series. So now what is actinoid series? Here we have, after lanthanum we have actinum here. Do you remember I had shown initially this thing, actinoid. Here in lanthanide we have 5f orbital filling, and whereas in here we have 6f 6f 4f orbital filling, whereas in actinoid we have 5f orbital filling. So the question is, in actinoid we have 5f orbital filling is greater, so decrease in size from left to right in actinoid series is greater and gradual than in lanthanide series. So they are saying when we move left to right for lanthanide, first is lanthanide, right? In periodic table lanthanide series comes first and then comes actinoid series, and they are saying that from left to right atomic series radius of actinoid decreases very fast, it seems, than that of lanthanide. Why? Because actinoid has 5f orbitals, whereas lanthanide has 4f orbital. We know f orbital is a poor shielder, but we have 5f, n shell is more the n shell, due to the 5f is more, so we have, that is the reason actinoid has greater and gradual atomic radius, decrease in the atomic radius. So the correct option is 5f orbital have poor shielding. Hope this is clear. If you have any queries, comment down below. Thank you.